In this video, we're going to do some rather difficult gas problems. So I'll start with the first one. 3 bulbs are connected by tubing, and the tubing is evacuated. The volume of the tubing is 45 milliliters, and evacuated means that initially the tubing has no gas in it. So it's empty tubing, and it has 45 milliliters of volume. The first bulb that the tubing is connected to has a volume of 31 mils and contains 4.54 ATM of argon. The second one has this volume and this pressure of neon, and the third one has hydrogen. If the stopcocks, meaning the valves that are isolating the bulbs from the tubing, were opened, what is the final pressure of the whole system? Okay, so basically you have 3 gases, and it's important to understand or to illustrate how the system is prepared. So you have tubing, and then on the end you have valve 1 and here's the valve 1. You have, that's not a very good picture, but you get the point. And then you have valve 3 with the third gas in it. So once these, so they each have a P and a V. So we'll put this P1, V1, let's call them P and V, because we're going to end up using 3 separate equations. So you have a PV for each one. Once the stopcocks are turned on, all of this gas from all 3 will then be equally dispersed in the entire system. So that would be our final volume for the system. And we can just use Boyle's law for this question. And Boyle's law is P1 V1 equals P2 V2, representing the inverse proportionality between pressure and volume. So you can set up a P1 V1 for each of these gases and a P2 V2 for each of these gases, because you are looking for that final pressure. So the reason why, and this is another aside, but the pressure and volume multiplied together of an ideal gas is proportional to its moles. So that goes by the equation PV equals nRT. Let's say R we know is a constant and T is a constant. Then P is directly proportional to the moles. So we can, for all intents and purposes, say that the value of PV is equal to or proportional to the amount of gas we have. That's very important for a lot of other questions, but just keep that in mind. So for this specific question, we have 3 separate PVs, and we're going to see the final pressure of each one of those gases when it evacuates into the rest of the system, and at the end of the day, add all of those partial pressures up, because we know from Dalton's law of partial pressures that PT equals P1 plus P2, etc., as you add all the different partial pressures of different gases. So let's do that. So you have, for the first one, let's just go right through it. So the first one you have argon, right? And P1 for argon is 4.54 times your V1, which is 31, equals your P2, which is unknown, times your V2, which V2 will be the final volume of the system. So in that case, you have to add up all the volumes, including the tubing. So that'd be 45 plus 31 for the argon, plus 250 for the neon, plus 39 for the hydrogen, and that equals 365. So this is how you solve each of the P1 V1s. So we'll do the first one. We'll call it PA because it's for argon. So to solve for PA, you're going to divide by 365 on both sides, and you end up with, let's see, 4.54 times 31 divided by 365, and you get the partial pressure for argon equals 0.398 ATM. Okay, and we're going to repeat this process for the remaining 2 gases. The first one being neon. So neon has a P1 of 2.78. Its V1 is 250. Its P2 is unknown. We'll call it PN for neon. And V2, we know, is the same as the entire system, because once these stopcocks are released, the gases will evacuate into the entire system. So we have 365. So divide again by 365, 2.78 times 250 divided by 365, and you get PN equals 1.904 ATM. And we do the same thing for the last one, which is hydrogen, so we'll call it pH. So we'll do for P1, V1, so P1 for hydrogen is 8.85. V1 is 39. P2, we'll call it pH because it's the partial pressure of hydrogen. And then V2 is our 365. So once we do the same process and calculate pH, we end up getting pH equals 0.945. So the final step and what the question is asking for is what is the final pressure of the whole system? So then you would simply add up pH, PA, and PN. And your answer would be 0.398, let me see, 1.904, and you get 3.247 ATM. Okay, hopefully that makes sense to everyone. If not, you can rewind the video. All right, next. So what is the mass of water in grams formed from the reaction of 2.6 liters of hydrogen gas and 2.07 liters of oxygen gas? Both gases are at this many torr and this many degrees Celsius. Okay, so when they give you that, and whenever in a gas problem they're asking for grams or for moles, automatically think PV equals nRT. Even though Avogadro's law involves moles, still most of the time you're going to be using PV equals nRT. So let's write this down. And we have two gases in this case. We have hydrogen and oxygen. And we know they're talking about water too. So we seem like, all right, it's a reaction. So whenever they use the keyword reaction or they're combined to produce, things like that, or they react, then we have to write a chemical equation. So we can do that. So it would be it would be H2 plus O2 yields H2O. And we can balance it. We can put a 2 here and a 2 here to make it balanced. The first thing we would do is write a P1V1, a PV for each gas. So hydrogen gas, we have the pressure is going to be 771 torr because we know the pressure of both gases is 771. So we write 771 over 760 because we need all the pressures to be in ATM. The volume is in liters, which is 2.60. N is what we don't know. R is 0.08206. And T, temperature, which is 21.5 plus 273 to make it in Kelvin. So we can solve this, and I'll do it real quick on my calculator. Times 2.6. So on the left side here, you get 2.637 equals 21.5 plus 273 times 0.08206 equals N times 24.167, and you divide. So you get 2.637 divided by 24.167. And N you get, for hydrogen, you get 0.109. Okay, so that's good. Next, we're going to do the same exact thing for oxygen, and then we're going to see how many moles we have, and then which one's limiting, and then how far the reaction goes. So for oxygen, we're going to do the same thing. So we have, again, 771. So let's just convert this right here. 771 divided by 760 is 1.01 ATM. The volume is going to be 2.07 liters. Volume is going to be 2.07 liters, which is going to equal N times R, which is our 0.08206, times our temperature, which is 21.5 plus 273, which is 294.5. Okay, so let's solve for N one more time. And once we do that, then we can see our molar quantities. And I end up with N equals 0.0865 moles of O2. Okay, let's see how many moles are made of the product to see which one's limiting. So for hydrogen, we know that 0.109 moles, based on our molar ratios, 2 moles of hydrogen gas makes 2 moles of water. So we know it's a 1-to-1 ratio, or 2-to-2. So we know that based on the amount of hydrogen we have here, it's going to make the same amount, 0.109 moles of water. For oxygen, what we're going to have is we have our starting material, which is 0.0865. And we know based on the ratios that it's a 1-to-2 ratio now. So now we have to multiply this by 2, because if 1 mole of oxygen creates 2 moles of water, then 0.08 moles will make double that. So we take our 0.0865, multiply it by 2, and we get 0.173 moles of H2O. So if you recall from limiting reactant, if that's the case, we need to pick the reactant that produces the least amount of moles, so which is hydrogen. That's the limiting reactant. And our question is, how much is the mass of water? So we're going to use hydrogen, and to figure out how much product is made, which we already did, which was 0.109 moles, and easily convert that by multiplying by the molar mass into grams. So we take our 0.109 times 18, and we would get 1.962 grams of H2O. Okay, good. If you have any questions on that, you can comment below. Okay, let's do the next one. So calculate the total pressure in ATM in a 1 liter flask that contains 2.05 grams of neon and 8.38 grams of argon. The temperature of the gases is 24 degrees Celsius. Okay, so let's immediately convert this to Kelvin, because we know all of our gas equations need Kelvin as our temperature. So we can convert that by adding 273, and we get 297 degrees Kelvin. Okay, so next we have grams involved. We can figure out the moles. And then we can also figure out, using PV equals nRT, what that total pressure is. And we can assume all of these are ideal gases as well. And this helps us a lot, because we assume they're low enough pressure to be ideal gases. So let's do this. So the molar mass of neon is 20.18. So we're going to do 2.05 grams of neon divided by its molar mass, which is 20.18, 0.102 moles of neon. And then for argon, 8.38 grams divided by its molar mass of 39.95 grams per mole. And that's going to equal 0.2097 moles of argon. Now, it's asking for the total pressure in the system. And now what we learned about pressures is, if you add up, so we know something about pressures, that when we talk about partial pressures, we know if we add up the partial pressures, we get the total pressure. We also know that the mole fraction is correlational to the partial pressure fraction of an ideal gas, meaning that the gas molecules themselves are so small compared to the distances between them, their size is negligible. And we can just say that the entire gas sample, the ratios of each of the gases, correspond to the direct pressure ratios of the gases, because their size doesn't really attribute to their pressure at all. So what we can say, what this means, is that we can add these moles together to figure out the total moles of gas. If we were being asked for a partial pressure, that's a different story. In that case, we'd have to do 2 individual PV equals nRTs to figure out the partial pressure of each one. But since we're figuring out the total pressure, we can simply add up these moles, because we know that their size is negligible and all of the gases count the same. So we can take both of those mole numbers and add them up to get 0.318, and this would be, I'll call it NT, meaning moles total. So now we can take this number and we can do the pressure, which we don't know. The volume is 1 liter, equals N, which is our NT, 0.318, R, which is 0.08206, and the temperature, which is 297 Kelvin. No, not 27, 297. And we can solve for P by really just multiply. Since the liters are 1, we can just multiply everything across. We would take that number times 0.08206 times 297, and you end up with 7.598 or 7.60 ATM. and this is for the pressure total. Okay, great. So I hope that makes sense. If you have any questions, again, post in the comments, and be sure to like and subscribe to this channel.